Hi guys, this is Geometry, Lesson 7-2, Similarity Transformations. In this lesson, we'll be able to determine whether figures are similar. So similarity is not the same as congruent. That you need to note. Let's start with critique and explain. Helena and Edwin were asked to apply a composition of transformations of A, B, C, D. Okay, so they have their own graphs and they both do a transformation. Okay, but they both start with the figure A, B, C, and D. Part A, is there a composition of transformations that maps A, B, C, D to the second figure in each student's work? If so, what is it? Let's look at Helena's. How did this figure become this figure? Okay. Do you think C is mapped to W? I don't think so. Z to W is not corresponding to B to C, right? So that part, line CB, BC, would be corresponding to XY. So what happened? It seems like the figure rotated. And also the figure was enlarged. Okay, so how do you know how big it became? You can look at the distance between the sides, the corresponding sides. So BC is 2 units away. XY is 4 units away. So you can see that the figure was enlarged by a scale factor of 2. Okay. So let's note that this is 2 units and that's 4 units. So from CB to XY, you multiply by 2. You can also check other distances using the coordinate points. But we can see that Helena's figure rotated and dilated by a scale factor of 2. For Helena, rotate A, B, C, D 180 degrees and then dilate with a scale factor of 2. Okay, what about Edwin? Edwin's doesn't seem like it's rotation, right? C maps to H, D maps to J, A maps to F, and B, wait, no. Wait, okay, so, okay, that looks like B, that looks like C and B. Which one is the longest side? Could we reflect and enlarge it? Because then your figure should still have a straight line over here, right? Okay. And then you need to enlarge it. But do you see any relationship? The proportions are not right. So what can we say about Edwin's? There's no composition of transformations for Edwin's. They're not similar. Okay, for Edwin, there isn't a composition of transformations. Excuse me. Okay, part A, for each student whose work shows composition of transformations, which is Helena, describe the relationship between the figures. What are the relationship between these two figures? Can we say they're congruent? The figure itself is not congruent, but the angles are congruent. What about the sides? The sides are proportional, right? So what do we say? What kind of relationship can we say? That's when we say it's similar. And we'll talk about that more, but let's describe first. The side lengths of WXYZ are 2 times the side lengths of ABCD, and corresponding angles are. Okay, what else? The vertices of WXYZ same orientation as the vertices of ABCD. Figures a rotation point halfway between Z, or the things that you can write down. Okay, so in this lesson, let's think about what makes a transformation a similarity transformation, and what is the relationship between a print image and the image resulting from a similarity transformation. Let's look at example 1. Graph a composition of a rigid motion and dilation. Do you remember what rigid motions are? In the transformation section, we learned that the rigid motion preserves angle measures and distances between the points, right? So you can do reflection, translation, and rotation, and they all preserve angle measures and distances between the points. But dilation is different, right? Dilation preserves angle measures, but it does not preserve the distances between the points. So dilation is not a rigid motion. Let's look at this graph. If line M, M is represented by the equation x equals -3. So that's M. What is a graph of the image? Reflection over line M of dilation by a scale factor of 0.5 of the triangle ABC. So here we got a composition of a rigid motion and dilation. What do you do first? We learned the notation, how to read a notation in the transformation section. What do you do first? Do you do the rotation, the reflection first, or the dilation first? The one closer to the triangle, okay? Reflection of dilation means in order to do reflection, you already need to have a dilation, okay? Reflection of dilation, okay? So you need to do dilation first and then reflection second. Okay, so dilate the figure by 0.5 on the origin, right? Because there's no point that's given, that's specified. So if you don't see any point on the dilation notation, you're gonna dilate by the origin. Okay, and then that's your ABC prime. And then you're gonna reflect over line -3. And you need to go the same distance from the point to the line across the line, okay? And then that is your final answer. after this composition of transformations. Okay, so let's try number 1, A and B. The vertices of triangle XYZ are 3, 5, negative 1, 4. Z is 1, 7. So see if you can you can graph this composition of transformations for parts A and B. See if you can do it by yourself. Come back when you're ready for answers. Okay, so this is triangle X, Y, and Z. So part A, you translate the figure first. 1 unit to the right, 2 units to 2 units down. So let's do the first one. So the first one, part A, dilation by the scale factor of 2 out of translation 1, negative 2. Right, so first from here, you go 1 unit to the right, 2 units down. 1 unit right, 2 units down. 1 unit right, 2 units down. So that's your X prime, Y prime, Z prime. And then you dilate the points by the scale factor of 2. So from the origin, right? So Y prime prime would be here. X prime prime is going to be 6, 7, 8, 9, 10. And then 2 more. Okay. It's here. And then X prime prime. So it was horizontally 4 units away. So you need to go 4 units away more. And then, wait, it's not there yet. And then vertically, you're going to go from here. We're going to go 3 units up because 3 times 2 is 6. And then 4 times 2 is 8. So it's 8, 6. And so 8, 6 for X prime prime. And then, so that's equal to X prime prime, 8, 6. You need to know the coordinate points. Y prime prime, 0, 4. And Z prime prime, 4, 10. Okay. What about part B? Let's use green for part B. Part B is dilation of scale factor of 3 of rotation 90 degrees. If it's positive, that's counterclockwise over the point O, so origin, triangle XYZ. Okay, so you rotate this figure, the XYZ, 90 degrees from the origin. Okay, so what do you do when you do 90 degrees? What is the rule for coordinate points? What's the rule? Okay, your X and Y switch coordinate points, okay? And then which one becomes negative? The new X coordinate. So like your Y is going to be negative Y, but on the X coordinate point. So for rotation 90 degrees, the rule for your any point X, Y is negative Y, X. Okay, so your X prime becomes negative 5, 3. Y prime becomes negative 4, negative 1. And Z prime becomes negative 7, 1. Okay, -1, -1, 2, 3, 4, 5, comma 3, 1, 2, 3. Okay, that's x prime, and then -4, comma -1, y prime, and then z prime, -6, 7, comma 1. So z prime is here. Okay, you rotate it 90 degrees. And then what do? Dilation by a factor of 3. So that means you just multiply all your factors, all your coordinate points by 3. So after the dilation, your x prime prime becomes what? -5 times 3 is -15. And then comma 9. Y prime prime is -12, comma -3. Z prime prime becomes -21, comma 3. Okay, so if you draw that, it's gonna be a big one over here. It's gonna go outside a graph, so I'm not gonna graph that, but that is your coordinate points, and that's gonna be your answer. Okay, so part A, it's 8, 6, 0, 4, 4, 10. Part B is -15, 9, -12, -3, and -21, 3. Okay, remember how to do coordinate points for transformations. Okay, going back. Example 2, describe a composition of rigid motion and a dilation. Is there a composition of transformations that maps triangle XYZ to triangle JKL? Okay, explain. Is there a composition of transformations that maps XYZ to JKL? So first, we need to know if the sides are proportional and the angles are congruent. Okay, they appear to be the same shape, but different sizes. They're also positioned differently. So you know there must be a dilation. Okay, notice that Y here is on the first quadrant, but the corresponding point is K, and it's like on the lower right of the third quadrant. So it seems to be rotated. If it's a reflection, then you probably have similar positions, but your point K should be facing upwards if you have a reflection on the y-axis. If you have a reflection on the x-axis, it should be on the lower left if you do a dilation and maybe translation, right? So it must be a rotation. And then you just move it counterclockwise, probably 180 degrees. Okay. And then it's dilated. So move it 180 degrees and you dilate it from the origin. The scale factor is 2, if you look at the points. And you can write the rule using the notation. D sub 2 of R, small letter R, sub 180 degrees, comma 0 or O, maps triangle XYZ to JKL. You do the rotation first, rotation of angle, and then point of rotation are the information that you need to write. And for dilation, you need to write the scale factor. And if you don't write the point of rotation, dilation, that means you dilated from the origin. So in this case, you don't need to write it. Okay. Try number 2. So if the transformations in example 2 are performed in the reverse order, if you do dilation first and then rotation, are the results the same? Do you think your answer holds for all compositions of transformations? Explain. Are the results the same? So if you do dilation first, okay, by a scale factor of 2, so x goes here, x prime, now y prime goes 1, 2, 3, 3, 1 over here, y prime, and then z 4 units away, and then up 1, gonna be about here. So that's a dilation of 2. And then you rotate 180 degrees and it's gonna be the same. Ooh, but does it always work for any type of transformation? No, the order does matter, okay? So the first answer is yes. Okay. After the rotation, after the dilation, the triangle will have the coordinates x prime 4, 2, y prime 2, 8, z prime to be 8, 2. Okay. Rotating this 180 degrees, we get x prime prime to be -4, -2, because you're rotating 180 degrees, all positives become negatives, negatives become positives. Y prime prime to be -2, -8, and z prime prime to be -8, -4. Okay. Which are the same as the coordinates of triangle JKL. Okay, and does this answer hold? So changing the order, does the changing order preserve the results? Does it hold the results? Is it always going to be the same results if you change the order of the transformation? No. If you translate and then rotate about the origin, the result is different. So this is one example, that if you rotate and form the same translation. Okay, so dilation and rotation, for only dilation and rotation, the order doesn't matter because you're multiplying and then changing, multiplying by the scale factor and changing your signs, or your coordinate points, the placements. Okay, but translation does matter. Reflection does matter. Okay. All right, let's look at example 3 on the next page. Find similarity transformations. Why is PQRS similar to GKJH? A similarity transformation is a vocabulary. It's a composition of one or more rigid motions and a dilation. A similarity transformation results in an image that is similar to the pre-image. Okay, so this is what we've been looking at. The shapes are similar. They're not congruent because obviously the sizes are different, but they're similar. The shapes look the same. It's just the size that's different, right? So similar transformation results in an image that is similar to the pre-image. Okay. Measure the angles of figures to determine that angle S corresponds to H and R corresponds to J. The orientation is reversed. So P is corresponding to G, Q is corresponding to K. So it's reversed, orientation reversed. So the rigid motion includes a reflection. And then you have a dilation. Okay. So composition of a reflection, translation, dilation maps PQRS to G, K, J, H. So they're similar. Okay, as long as you can use the composition of transformations, they're similar. Now, are they congruent? No. In order for the shapes to be congruent, they need to be able to have composition of transformations that are rigid motions. Okay, dilation is not a rigid motion. So if it includes dilation, the shapes are similar, they're not congruent. Okay, so we have similar properties for similarity too. Okay, similar properties to congruency properties. We got reflexive property of similarity. So A is similar to A by itself. Symmetric property of similarity. If A is similar to B, then B is similar to A. Transitive property of similarity says if A is similar to B, B is similar to C, then A is similar to C. Okay, so symmetric changes the order. Transitive is jumping or substituting your parts. Let's try number 3. Describe a possible similarity transformation for each pair of similar figures shown, and then write a similarity statement. So first, write the transformations that you might need to map the black figure to the red figure, okay? The pre-image to the image. And then write a similarity statement, which are similar to which. Okay, so for A, you might say, so look at the orientation. Is it a reflection? Does the orientation change, flip? No, it kind of looks like it rotates, right? It rotates counterclockwise. And then it doesn't look like they're the same size. You have to dilate. There's a dilation. You might have to translate as well. Okay, so rotation, translation, and dilation may be the transformations that you might use. The similarity statement just means, right, which one is similar to which one. Triangle ABC is similar to triangle A prime, B prime, C prime. That's it. Okay. So part B, how can you describe? Looking at the orientation, which points are corresponding to which point? So Y corresponds to Y prime, Z corresponds to Z prime, W, W prime, and then X to X prime. So Z was on the top in the pre-image, and now it's on the bottom. So what can you say? This involves a reflection over the horizontal line. So reflection, what else? Dilation, because the size becomes smaller, it shrinks. And then you need maybe translation, it depends, but you can just write reflection and dilation. And similarity statement, WXYZ is similar to W prime, X prime, Y prime, Z prime. Okay, so these are the answers. Okay, let's look at the next page. Example 4, determine similarity. Can the artist copy her sketch to cover an entire wall measuring 15 feet high by 20 feet wide, so her wall mirror is similar to her sketch? Explain. If the artist can map her sketch onto the wall, then she can place her sketch at the bottom left corner and dilate it. So the smaller rectangle here, if it dilates from this point, is it gonna be similar? Is it gonna be proportional? So you need to see if 14 to 15 feet, 14 inches to 15 feet is also proportional to 11 inches to 20 feet. In order to do that, first you need to convert the inches to feet or feet to inches so that you're comparing the same measurements. So convert the dimensions. 15 times 12, 1 foot is equal to 12 inches. So you times 15 by 12 to get 180 inches. And then, so that's 180 inches. 20 times 12 is 240 inches. Okay. So is 14 over 180 equal to 11 over 240? If they do, okay, that's a question mark. If they do, then they're proportional. They're proportional. The distances are proportional, so they're similar. Okay, so if you divide both of them, they're not gonna be proportional. So the sketch cannot be copied to cover the entire wall. Is the answer. Okay, unless these answers are exactly the same, they're not going to be proportional. So it's not similar. So try number 4. Suppose the artist cuts 2 inches from the width of her sketch in example 4. How much should she cut from the height so she can copy a similar image to cover the wall? So from her sketch, she cuts 2 from the width. So 11 minus 2, which is 9. And then how much does she need to cut from the height? So h, the length. Wait, width is 14, never mind. Width is 14, minus 2 is 12 inches, and your height is 11. How much? You're getting x, so that it's proportional to the wall. So width has to be proportional. 12 has to be proportional to 140. And in order to be proportional to the height as well, you're finding a number that's proportional to 240 inches. Why did I write 140? It's 180. Okay, 180 and then 240. All right, so your n should be multiplying 240 on both sides. Your n should be 12 times 240 divided by 180. And that's equal to what? Well, first you can simplify these numbers. Divide by 2, divide by 2, divide by 3, divide by 3. 2 times 240 is 480. And in order for you to have, that does not seem right. Right, 240 times 12 divided by 180 is 16. Okay, divided by 3 is 16. So then, in order for this to be, your height to be 16, 11 minus what? Okay, so I made a mistake here. So scratch everything except this part. So I switched. The height and the width, the wording is a little bit confusing. Okay, so this is the height. That is the width. So we subtracted 2 from the width, 14 minus 2. Okay, we did that part right. Height, 11 minus something. But the proportion that we made, height, 9. Oh, wait, no. Height, which is, no, the width, which is 12 now, must be proportional to 180. Wait, do we need to switch? Okay, maybe. Oh, I see. Okay. Yeah, so it's actually, I think I flipped the explanations too. Sorry. So that's 11 and that's 14 because this one is the bottom part, right? So it needs to map here to 240. So 14, yeah, 14 maps to 240, 11 maps to 180. There you go. And so that one is not actually mapping to 180. It must map to 240 and then n over 180. So you're going to multiply 180 on both sides. And then n is equal to 9. So in order for the height to be 9, you need to subtract, you need to cut 2. So 2 inches from the height, it would be the answer. Okay. Yeah, so sorry for the confusion, but you need to make sure which maps to which and don't mix up the fractions. So this part is the length and the wall, the width is the length of your paint. Your height of the painting is this part. It needs to correspond to the correct one. So the height corresponds to this one. Okay, that's a common mistake and I'm glad we went over it. Let's look at our last example. Example 5, identify similar circles. Write a proof that any two circles are similar. Okay, given that circle P, center around P with radius R, with a radius S for the circle that has a center of Q. Okay, prove circle P is similar to circle Q. Are the circles similar? First of all, do they have the same angle? Yeah, all circles have 360 degrees. Are the radius proportional? That's what we're gonna look at. Translate P to Q, and then you'll see that it maps here, right? And then it coincides with Q, and then you'll find the scale factor that dilates point P to the radius R to the radius S. Okay, so S, K is equal to S over R. And that is since there's a scale factor, it's a dilation. So since the similarity transformation exists, the circles are similar. Okay, so all circles are similar, like you would already know, but this is why you can prove it using dilation and translation. Write a proof that any two squares are similar. How do you know all the squares are similar? Because they all have right angles and all the sides are proportional, right? There's a scale factor that maps all the corresponding sides. Whoops. Or all the corresponding sides to the corresponding to each other. Okay, so if you're given square ABCD with side length R and square EFGH with side length S. You can prove using square ABCD is similar with square EFGH by saying translate square ABCD to square EFGH. So A prime coincides with E. Then find the scale factor. K equals S over R. That maps square ABCD to square EFGH. Side length S. Since a similarity transformation exists where ABCD is similar to square EFGH. This holds true for all and circles. But this is a proof for a square, for two squares, any two squares. There. Okay, let's summarize our lesson. Similarity. A similarity transformation is a composition of one or more rigid motions and a dilation. Okay, composition means there's more than one. Two figures are similar if there is a similarity transformation that maps one to another. All circles are similar to each other. All right, that was lesson 2, similarity transformations. We'll continue with our next lesson, proving triangles similar in the next video. Bye.